So, hi everyone, I'm super excited to be here. I am really very excited to be here. My name is Tamar, and today I'm going to share with you a little bit about my voyage with working in scale. Oh, I forgot my clicker. So, my name is Tamar Rushem. I started as a software engineer almost 15 years ago. I worked mostly in the States in a variety of companies, different technologies. I did my master in mathematics and computation. And 7 years ago, I moved back to Israel and I started working for GoDaddy. So GoDaddy doesn't have offices here in Israel. I started in an all-remote team way before COVID. And after about 2 years, I became the team lead. And my team and I, we built a brand new product. And after it was globally released, and I felt, it was well underway for growth, and I felt it was my time to move on and start my own entrepreneurial, voyage, I guess. And I opened my own startup. I built an app for parents to manage the family schedule. I'm sure if there are parents here in the audience, they recognize the need. But after a year and a half, I haven't found the product market fit. It hasn't reached the scale that I wanted it to. And so I recently joined Edge Gaming, where we are building a platform for analyzing and training professional esport players, something yet again completely different. So that's a little bit about myself. And today is going to be in 3 parts. First of all, I'm just going to give you the premise. So what was the problem? What were we trying to solve? And then I'll walk you through the different things I tried in looking for a solution. The stack that we use, like Amir mentioned, was in some ways, there are similar lines to yours. So I thought it would be interesting to kind of take you through the different configurations of stacks that I've tried. And then last but definitely not least, I'll share a few of the challenges and my key takeaways and, what I think is really important in different types of working in scale. Because at the end of the day, unless you're doing a very out-of-the-box scale solution, you're going to have to find your own. But I still think there's value in learning from other people's experiences. So what is the premise? So we had a table with over 1 billion records. It's not too bad. It's not huge scale. There are some things we can pull. But the data was highly relational and heavily indexed. Still not a big deal. There are still some things that we could do to make it work in SQL. It was all in one SQL table. However, to add to that, some of the data was variable fields. So each user could define their own fields, and that data was stored in a blob. Okay, so what do I mean by additional fields? Let's say, for example, that our users were publishers, and each publishers had their books records, many, many book records. So every book record would have a title and a subtitle and a price, but we also allowed these users to define their own field. So one publisher might say, I want a field that's country, and that's a string, and this other publisher wants a popularity scale, that's their own thing, and that's an integer. And those additional fields were in a blob. So to start off, we had this fairly large table, and we wanted that variable data to be searchable. So I'm sure to all of the engineers here, the wheels are starting to turn. How would you go about it? I mean, I think it's an interesting problem, and there are a lot of ways to solve it. But what happened at this point is that several other services in the company were like, oh my God, you're building this? This is awesome. We also have a similar type of record. And not only is it a similar type of record, sometimes it is the same record. It is the same book represented in different services. There is a duplication, and it would be amazing if we can make this into a central service that all of these different services interact for these records. And what that meant is several things. First of all, from a scale perspective, some of these services were smaller, but some of them were larger. So our scale is no longer 1 to 2 billion. It is much, much more. In addition, it means that those variable fields, the variation is even larger. Every service had a slightly different way of defining, interacting, and updating those records and managing those records. And last, but definitely not least, it meant that we had to be far more performant and reliable, because if we are just, one backend servicing the one product, if we fail or have a slowdown, it affects just the end users that are currently in front of our product. But once we've become a service that, in addition to just our end users, we also service these other services, these other products, if we fail or have a slowdown, we're now starting a ripple effect that causes slowdowns in all of these other products and services. Okay, so that is the premise. We have a fairly larger scale than we did when we set out to. And we have our fields, but also variable fields, and we want them searchable. So now I'll start going through what we did looking for a solution. The first technology that we knew we wanted to use was Elasticsearch, because we knew we wanted to use those search capabilities and expose them to our end users when interacting with this type of records. But we didn't want to use Elasticsearch as the sole only source of data or data store, because we've had issues with nodes being down, data being corrupted, packets being lost. And so we wanted to have also a source of truth. So in case Elasticsearch is down, we can have some very basic querying, or we can do some, we can restore Elasticsearch from it. And for that, we chose Cassandra. So Cassandra, as I was told you all know, is a NoSQL with a SQL-like on top of it. It's highly scalable, and it's optimized for writes, and we want to mostly write into it. That was the idea, at least. And then do all of our reads, or most of our reads, from Elasticsearch. We also wanted it for its cross-data center replications. So we had Elasticsearch, we had Cassandra. Are we done? Can we take our requests from the web and from the REST APIs and just write them into Cassandra and Elasticsearch in return? Obviously, that's not a viable architecture, because if requests come from two different sources, if a request fails in the middle, if at the end of the day we have two different records in Elasticsearch and in Cassandra, if there is a difference, how do we know which one is true? How do we know which one should update and which one should stay the same? So we started looking for a way to combine these two in a reliable way. And first I looked at out-of-the-box solutions. Keep it simple, make it easy. The first thing I looked at was a project called Alessandra. It's an open source project, and it is exactly as the name suggests, Elasticsearch and Alessandra merged into two. At the time, it was a not well-maintained open source. It was on older versions of Elasticsearch, and we felt like it wasn't mature enough for us to use it as a solution for this. However, today, from what I've seen, it has grown. It even has commercial support. It is currently up to date from what I've seen. So maybe today it could have been a nice option, but at the time it wasn't a good choice for us. The next thing I looked at was DataStax Enterprise. So DataStax, the company that provides Cassandra, also has an enterprise solution. And this enterprise solution has a variety of things. It has graphs, analytics. It also has search. It has extensive search capabilities, almost matching the Elasticsearch capabilities. I don't know how they implemented under the hood, but if we worked with Cassandra, we know that that is not how Cassandra comes out of the box. So they definitely did some work. I give it a try. It had, like on the trial version, it had a very easy API. It did everything that we needed to do. And I went to my boss and I said, awesome, like this looks great. I think we can use this. But then in a conversation that he had with the DataStax sales team, we realized that this enterprise solution was a little outside of the scope in terms of price, because we couldn't just take the searchability. We had to take the entire set of solutions, and it wasn't in the price range for this project. So no more out-of-the-box solutions. And we're like, okay, how should we build this stack reliably inside? And so we started looking at Kafka. So Kafka, of course, is a messaging queue. You put a message in, and it's scalable, and it's reliable, and you can replay, and it can be our source of truth. And we're like, okay, so from our application, we'll write into Kafka, and Kafka will write into Elasticsearch and Cassandra. And then Kafka doesn't come on its own. You have Confluent, which is like the it brands itself as like everything you need around Kafka, connectors, and so on. We also added Zookeeper for load balancing. We added the schema registry because, like we said, Cassandra has a SQL-like. It is strictly typed. So we wanted to make sure that the messages going into Cassandra were well formed. We also added like open source connectors and some things I didn't even put. And I kind of have this stack working on my dev machine. I have our prototype of our app, Elasticsearch, Cassandra, Kafka, all of these things, and it's kind of working. And I go to the data team, I'm like, okay, is this a stack? Can we like move forward with this? And they're like, yes, this is a stack, this is great. Just one little thing. We also need FluentD for monitoring and logging. So at this point, I'm trying to add FluentD, and I'm unable to configure all of these things to work well together. And what made it worse is that at this point, 2 other developers joined on the project. So I'm working on my Mac natively, and one of the other guys is trying to set all of this up on their Ubuntu VM. And then the third guy, smart guy, wanted to build a Docker component, Docker container for it. And we're all just stuck trying to configure this very complex setup. And nobody's doing any work. I mean, we're developers, I mean, we're doing work, of course, but we're not progressing with the application that we want to deliver. And so at this point, we're like, whoa, let's pause for a second, let's stop and reevaluate. Do we really need all of this stack? And the answer was no, we don't need another tool to be our reliable, consistent source of truth, because we already said that Cassandra is going to be our source of truth. So we wiped out, or we put aside all of this Kafka configuration and went with a much simpler stack. Right, the no. So what did we end up doing? So we have our requests coming from our web and our REST APIs, and when they come, they write first and foremost into Cassandra. So when the response returns, we know that Cassandra, our source of truth, is updated. We also write into Sidekiq, which is our backend worker job manager in Rails. And so after the request has returned, the job is processed in the background, writing into Elasticsearch. So we're eventually consistent. And we've decided this is a stack that is fine for us. It is okay with us that the users or the services update a record, and that it might take a little while before the reads are accurate. They might get old data, and it might take a little bit of time before they get the most up-to-date data. Okay, oh right. Before that, I wanted to talk about CAP, about what does it mean, or what did it mean for the app to be eventually consistent. So CAP theorem says that in a distributed data store, you can only guarantee 2 out of these 3 promises. You can either be consistent, meaning that you will always return the correct answer, or you'll return an error. You can always be available, so you'll always return a response, no matter what it is, but it might not be the most up-to-date one. Or you can do partition tolerance. Well, you always guarantee at the end of the day partition tolerance, which means packets won't be lost. So what you're left with in a distributed data store is a decision between consistency, and that you might get an error, but the answer will always be true, or availability. And like I said, we decided to be available all the time and eventually consistent. But what I think we didn't quite understand at the time, or what now when I look back at the project, I really realize it explicitly, is that, often projects like this one, they start with a single, usually SQL, one data store on one server. And we really don't appreciate all the capabilities that come with it. All the things you can do with Atomic. And what I realize is that when you transition into a scalable distributed solution, you're going to lose some of that functionality. You're going to lose some of the things that, you lose some of the things that you take for granted, or we took for granted, when having just one data store on one storage server. Okay, so we have our stack, and we've made our choices with availability and consistency. And that's it. We're happy. We can launch, and it's all going to be smooth sailing from now on. And now comes what I like to refer to as an infographic, because I feel it really gives you information about life, where you have a plan. And then, especially in software, users are going to put ponds somewhere, and then hail is going to come down, and you're going to be like, why would anyone ever do this? Because no plan ever survives its first hit with reality. So what happened after we launched? Here comes the challenges and takeaways. So the first challenge I wanted to share with you is something I like to call Elasticsearch is schemaless. Well, yes, but actually, no. Yes, Elasticsearch is schemaless. We can put whatever documents with whatever fields. However, if you want to search these fields, you need to create a mapping. This is from the Elasticsearch documentations. And the mapping, if you see at the bottom here, defines a field name and its type. Now, I don't know, but to me, it looks like a schema. You have to define what type your fields, what are they going to be named, and what is their type in order to search on them. Now, why is that even a problem? I mean, it's a fairly reasonable requirement. But if you remember, we had our variable fields. So our records looked a little bit like this, where the last field could be country, could be author, could be comment, and it would be a string. Now, how can we take all of these different documents and then make these different different fields searchable? Now, the naive solution would be, of course, to just add another mapping for every such new field. We'll have a country mapping, we'll have a popularity mapping, but it works in a smaller scale. It obviously wouldn't work in a larger scale. When you add so many indexes, you're going to suffer, and your cluster is it's going to stop working eventually. And not only Elasticsearch, even Cassandra has a limitation on how many columns you should add before it starts having performance issues. And so the solution that we did for this problem is that we created a mapping per user, which referred to string 1 and int 1. So for me, string 1 could be country, and for this other publisher, string 1 could be author, like we said, and all of them would go into the same index, and now we can map. Now, it's a fairly, I thought at the time, fairly elegant solution. It wasn't very hard to implement either. We had like a mapping table, and each user had the mapping, and then we had like a converter when we read and when we wrote. But the thing is that this little layer actually ended up adding quite a bit of complexity every time we interacted with writing and reading, because we always had to take into account those mappings. And so, especially when working in scale, though it's, I know now, always true even when you're doing a small little startup that's just starting, when you add a little bit of complexity, it tends to scale especially. So it comes with a price. The next challenge that I wanted to bring up was relational data in Elasticsearch. Because, I said at the beginning that our data was relational, and Elasticsearch is a non-relational database. So what does it mean? Let's go back to our example. It means that, let's say that we have our book records. So we have all of these books, but we also have purchases. And one book can have many purchases. And that's great. So we'll have one index for books with all of those fields like we define, and one index for purchases with all of those index. But then we wanted to answer a very simple question. We want to see all the books from country Israel that were purchased in the last 30 days. But these are two separate indexes. There is no relation. We cannot do a join table like we would in SQL. So what are the different ways of solving such a problem? Well, the first option is to do an application-side join, is to query all of the books from Israel and all of the purchases in the last 30 days, and then keep them in memory and merge, sort, maybe paginate, which again is a good solution for a smaller scale. But when you have a lot of data, it's not something that's feasible or viable to do in memory. The next option is nested objects. And when we saw it, we were like, awesome, that's perfect. That's exactly what we want. Every book will have many nested purchases. But the problem is that nested objects which like its name means nested records within a record, it comes with a limit, a built-in limit of 30. And you can increase this limit, but there's a reason there's a limit and that it's so low. It's going to have real impact on your index if you have too many nested objects. The last and not least is denormalization, which I'm sure everybody here knows. It's when we're going to replicate some of the data, we're going to duplicate the data, and then we're going to use that. For example, we'll have a third index that maps all the books from Israel and all the purchases, like keep the fields, all the country fields and all the purchases, and then look up against that third index. So what we ended up doing, what we ended up realizing is that we don't actually need to answer what are the last 30 days. What we really need is the last 10 purchases of different types. So what we ended up doing is a combination of these last two, and we duplicated some purchases as nested objects in addition to the other index. And the real big takeaway here was that in distributed systems, you have to design for your queries. Now, when we start working with a distributed system, we all know that. We're going to have to design for our queries. But I think the interesting part came when I was chatting to our product owner one day. And he was like, well, I might want to ask about, the books in the last 30 days, but then maybe in the future, I might want to ask about this other criteria or have this other query. And what I realized is that that shift in thinking that we have to design for your queries, it doesn't stop in engineering. It has to propagate as well to product, because at the end of the day, it's product that needs to say what queries we're going to answer. And it wasn't just in our little circles of engineers of how we're going to solve it. It goes back to that, what I talked earlier about the sacrifices and the choices we have to make. Because from our product owner's perspective, why couldn't we do it? I mean, we used to be able to query and slice and dice however we want, but suddenly we no longer have this, or we could answer this query, but it will require this amount of work. So this shift in designing for your queries is not only for engineering. It's a product, it's a much larger shift in thinking. Okay, so an issue that we all were curious about, at least, were performance issues. Obviously, naturally, we thought we're going to hit performance issues with our back-end workers and with Elasticsearch. But surprise, our performance issues were not where we thought they are going to be. I'm keeping you all in tension. Where were these performance issues? We have to know. Actually, the back-end workers, we were pleasantly surprised, worked really well. Honestly, by the time the users got back to their main page and it reloaded, the data was there. The only time we saw slowdowns was when one of the other services kind of migrated all of their records into ours and sent like hundreds of thousands of records in a few seconds. And then, yes, we saw slowdowns, but we scaled up our workers and it cleared up and it didn't have a real impact. So our performance issues weren't with that piece of the architecture. They honestly weren't with Elasticsearch. Where we've seen performance issues was mostly actually what happened before we wrote into our backend workers, what happened with Cassandra. But in order to explain it, I need to talk a little bit about the balancing of partitions in Cassandra. So the smallest piece of information that sits on a single physical device in Cassandra is going to be a partition. So you have your cluster, it has many nodes, even a node can spread over several computers. The smallest part is going to be the partitions. And when you define your record, the first thing is the partition ID that tells the system where to go look for your record. And the second one is going to be your ID. And when we got introduced into this concept, we were like, okay, that's an easy choice, right? The publisher is going to be the partition ID. So all of the publisher's data sits on one partition, on one single little thing. However, you have to make sure that your partitions are balanced. If one partition grows too large, it's gonna not only cause issues with that specific partition, it can bring down your cluster. And I think the recommended limit at the time was 100 megabytes. And the problem was that some of our users had a lot of these records. We even had one user with 10 million such records. So we said, okay, we have to balance these partitions so we don't have issues. And the solution we implemented was we created batches. So every publisher or every user can have multiple batches, and every batch has a limit of how many records it can have. And again, it sounds like a very elegant solution, and it's fairly easy to implement. But what happened at this point is that so remember, Cassandra is our source of truth. So when we get a new record, we need to know, is it a new record? Is it existing? Is it an update? Is it an insert? Have we reached the batch size? We have to start now querying. And first of all, our queries had several different elements. It wasn't just query by ID, because we didn't always have the ID. It was a combination of a few fields. For example, in a book, a title isn't enough to uniquely identify a book. Some books have the same title. So we'd need a combination of like title and author, for example. But suddenly we're across batches, and those queries are expensive. Not only that, whenever we add a new record, we need to calculate, have we reached the batch size? And honestly, it sounds like a very small question. I mean, coming from SQL, it's like just a count. It should be very easy for us to answer. But with Cassandra, doing a count is not such a simple question to ask. And what happened from the performance perspective is that our writes ended up being slow, because we had to do all of these querying, and we had to work around all of these restrictions around the size of the batches and querying across batches. And the real big takeaway for me from this was to solve for the 98%. So solve for the 98% means do the simple solution that solves a problem for 98% of your users, and for those other 2%, you can build them their own specialized solution. And for this scenario, we only had like a handful of users with that many records that it would have caused a problem. The vast majority of users didn't have these many records. And if we had solved for the 98% and left the partition ID as the user ID, we could have circumvented a lot of these. And then for the bigger users, we could have created a separate solution, a specialized solution, and it would have been simpler because our entire system wouldn't have been so complicated, and we wouldn't have everybody experienced the slowdowns, not just the large customers in this scenario. So now comes the question of, would using SQL have solved all of our problems, at least SQL instead of Cassandra? The answer is a little more complicated. I mean, yes and no. When you're working in scale, you're always going to have issues. It's always going to be a challenge. But I do think that in hindsight, when looking back, Cassandra was definitely not the right choice for this project. I mean, if you look today, this was at the fairly beginning of Cassandra, and there wasn't a whole lot of information out on it. And if you look today at what are the use cases that Cassandra is the right choice for, then it's pretty clear that this one isn't it. I also didn't mention, but given the nature of our records, we also had a high volume of updates and of deletes. And Cassandra is just not built for that. It's not the right tool for this job. So it was actually clear on a fairly early stage after we went to production and went live that the tool wasn't exactly right for our needs. But obviously, it's a young product and we need to make progress, we need to deliver, we need to grow it because it's not yet there. But we made plans to moving back to a sharded SQL, and after I left, they have shifted back into a sharded SQL. And I think that, using sharded SQL does have its own challenges that I'm sure they've encountered. I think for this project, it was the right choice, and that it was way easier to develop this against the right tool. But what could we have done then when we didn't have the knowledge? How could we have made a better choice? And here's what I think and what I recommend to startups, to teams in large companies, to anyone who's assessing and choosing a new technology, and that's risk management. So whenever choosing a new technology, I think it's better to do some assessment of risk. And risk has a few different factors. It's about how well you know the technology, how mature the technology is, how well established it is, but also how hard would it be to replace. So a few weeks ago, our product owner came up to me and he was very concerned about the technology we use for our archive files. So we have large files that we take and process, the game files, and then we put them in storage. And they're there. If we need to, we can grab them again to reprocess. And he was very concerned that it wouldn't scale, the solution that we used. And I tried to explain to him, it's S3, it's okay, we can scale with it, it's gonna be fine, but he still wasn't easy. He didn't felt good about it. And so what I told him was that, if we do get to a place where we need to change our storage for these files, we can do it fairly easily. The impact on the app won't be hard. But for something like a data store is actually very hard to swap, as we all know. And so the risk with choosing Cassandra ended up being much higher, not only because it was new to us and a fairly young technology at the time, but also because changing it had such a high price. And then also in risk management, or as another example, I wanted to bring this picture. I know that we haven't flown in a while, so I don't know if it's taking a second to what is in this picture? This is the food trays on planes. So you have the seat and then there's a little. So I was flying a couple of months ago actually, and it was a long flight. So at the end I'm dozing off, and suddenly I look at this thing, and I realize this little piece of plastic that's there. Now this piece of plastic, all it does is prevent the little valve from turning left. So the little valve can only turn one side where it used to be able to turn on both sides. And I was sitting in front of that little plastic valve and I was thinking, I could probably install one. I mean, I'm not an expert, but I'm fairly handy. I could give it a couple of tries. I could make this tiny little fix. But then I look up and I see rows of seats, hundreds of seats, and every single one of those seats have this tiny little plastic valve installed. And all the seats on the right-hand side had the valve on the left side, and all the seats on the left side of the aisle had it on the other side. And I just thought there on the plane that this is such a wonderful example of the price of small changes in scale. So we all know that airplanes and flights, that's huge scale, but it's very theoretical, it's very abstract. And I felt that this little thing is such a beautiful, concrete example, because I just think of the logistical nightmare of coordinating this across a fleet of planes and thousands of seats. And I wanted to take this as a point of talking about, the importance of tests. I feel that tests are always we always want to move forward and deliver more value to our users, whether it's a startup or if it's a big company. And especially, I think, in projects of scale, because scale is usually, let's face it, it's a technical task. If you're doing something to support the scale, it's usually not having a direct impact on your direct users. But, maybe if someone tested this little tray thing and they had said beforehand that they needed the valve to turn only one way, just thinking of how much headache, even QAing this thing, walking through the aisles, making sure all the seats have them, having another checkbox that says, yes, this has the little thingy that prevents it from turning. And so testing more originally, and I've seen it again and again and again, just helps you save more time. And I think we all know it, but it's often very hard to actually do it in real time. So last but not least, like I said at the beginning, in such solutions, you're always going to come up with your own crazy combination of what you need to do to solve your problem. I hope that this was still, useful and enjoyable at least. And thank you so much. Feel free to look me up to connect on LinkedIn. I'm not on Twitter or Instagram, but I'm happy to connect on LinkedIn. And that's it. Thank you. And I'm here for questions.
For your experience.
Yeah. So the question was when to know when to do work to increase scale of an existing app. So this whole project actually started as TickDit, right? So like I said at the beginning, we had this table, it was growing large, and we didn't want to get to a point where we actually have things or issues that impact the users. So we're trying to be preemptive about it, and I think that's the right choice. But the signs were the table becoming large and a little slow. So when I just started on this project, everybody was kind of like throwing around, this table is like 1 to 2 billion records, 1 to 2 billion records. And I'm like, okay, we enjoy throwing this number. How much do we actually have? So I went into the console and I typed, records.count, and I waited on the production console, of course. And I waited and I waited, and then I'm like, oh my God, what am I doing? Abort. So I think that, when your tables are starting to slow down on fairly simple queries, which is what we started seeing, I think that was the sign there. And for every project, it's going to be different. I think that in general, as a general rule, it is better, like here, to be preemptive. But I also think that there is some premature optimization. So again, going back to my current world, in startups, I sometimes see it where, trying to build from scale from the beginning, it's not necessary. Usually, most startups don't start in very large scale, and you can wait with this decision and write the simpler solution because it's harder to write for scale. So I think it's a very delicate balance. And I don't think that there's an absolute answer of like, this is the right time. I do think it was definitely the right time for this project.
Question?
Yeah, right. So the question was that the solving for the 98% creates a situation where you have these unique unicorn solutions only built for this little handful of users, and you need people who understand this unique solution and maintain it, and it can grow out of hand. And that's absolutely true. So again, I think like before, there isn't like an absolute answer. I do think that in this case, the slowdown and the impact was huge. And so in this case, at the end of the day, it's a matter of like, it's a matter of balancing the odds. I think that the 98%, honestly, almost always you solve the 98%, and it's really like you realize that maybe you don't even need that. Like you wait for the customers to say, oh, we need this, and then you'll see if it's a high enough priority, and then you'll build this. So in a previous company that I worked at, it was code libraries for C# and for Java. So it was compiled into, the product itself was code libraries that was compiled into C# and Java. And then Java was dropped. And then we had one customer that still paid for like a lifetime of Java support. I don't remember. And yes, we had to continue supporting them, but it was still minimal. Even having to have some people who know the specifics of this customer, it was still hugely beneficial than trying to maintain all of the Java support. Yeah.
Okay.
Thank you so much.
Thank you.